Welcome to the Solarworld cell production plant in Freiburg. This plant uses a fully automated process to manufacture multicrystalline silicon wafers. Our silicon wafers are inspected and cleaned before they enter the cell manufacturing area. Under clean room conditions, the wafers pass through additional cleaning baths, where every last bit of silicon sawdust or kerf that accumulated during the wire saw process is removed. These baths also contain a variety of chemicals that etch the surfaces of the wafers, a step that experts refer to as texturing. Zooming in on the wafer by a factor of 10,000, one can see how the surface structure changes. Countless dimple-like recesses become visible that give the future solar cells a larger surface area while minimizing unwanted light reflections. As a result, the cells can absorb more sunlight and generate more electric energy. Before this point is reached, however, our wafers must pass through a number of processing steps, the most important of which is probably a phosphorus diffusion step. In pairs of cells, placed back to back with one another, the wafers enter a tube furnace, where they are heated to over 800 degrees Celsius and diffused with phosphorus gas. This gas condenses on the open surfaces of the wafers. It penetrates the wafer and forms two layers with differing electronic characteristics based on their respective atomic structures. The base material is silicon, which previously was mixed with boron atoms during crystallization. Boron is used because it has 3 outer electrons, one less than silicon. A positively charged hole is thus created in the atomic bond. Diffused phosphorus atoms are slightly different. They have 5 outer electrons, which means one more negatively charged electron than silicon. The result? 2 different charge carriers, negative electrons and positive holes, that strive to achieve an equipotential bond according to the principle of opposites attract. The free charge carriers really get going when the sun's rays hit them. In sunlight, the photon's light energy virtually shoots large numbers of charge carriers from their bonds. This effect generates an electric field between a positively charged layer and a negatively charged layer. The charge carriers try to escape from this field, thereby causing the difference in potential to increase even further. If contacts are applied, the charge carriers will take the path of least resistance, which in turn generates a flow of electrons or electrical current, illustrating the photovoltaic principle. It takes approximately an hour to convert positively doped wafers into conductive wafers. The result is an electric component that transforms light into electricity. However, before you can actually take advantage of this effect, further production steps are necessary. Once again, the cells are cleaned and etched under the scrupulous supervision of our staff. The 0.2 mm thin cells are then placed in an acid bath, where only their bottom and edges are exposed to the acid. The effect, the positive side, the bottom, is electrically isolated from the negative side, the top. The solar cells then enter a plasma chamber, where they are given their typical color. The blue surface reduces optical loss by preventing unwanted reflections. As a result, more light can enter the cells, and more power can come out of the cells. However, to actually conduct electrical power from the cells, metal contacts are needed. Screen printing machines are used to apply a contact area with solder strips onto the backside and thin contact fingers onto the front side. High-performance furnaces then burn the contacts into the silicon. The solar cell is now permanently bonded with its current collectors. A conductive solar cell has been generated from a silicon wafer. Sensors check the cells once again for possible fractures, cracks, or other imperfections. Other measuring processes check the cells for their performance and other electrical properties. The best-known parameter in this regard is efficiency. Efficiency refers to how much electrical power a cell can generate when it is exposed to 1000 watts of artificial sunlight. Depending on the test results, classifiers sort the cells into 32 possible quality grades. Indispensable, the final quality assurance check. So far, machines have tested all parameters, but now our experienced staff is on hand to monitor the products. The solar cells do not receive the seal of approval from our experts unless they meet our strict quality standards. This is how Deutsche Cell in Freiburg manufactures around 1 megawatt of solar cells every day. Enough solar cells to power 250 homes. Solar cell production can hardly be any faster or more energy and cost efficient. This is what we at Solarworld stand for. We turn sunlight into power. At its Freiburg plant, Solarworld produces multicrystalline silicon wafers for the photovoltaic industry in accordance with the highest quality standards. The preliminary products for solar cells are manufactured in 4 almost fully automated production processes: crystallization, brick production, wafer fabrication, and wafer finishing. Ultra-pure silicon is used as the base material in the manufacture of multicrystalline wafers. The feedstock is placed into a mold made of fused quartz. With a load of up to 600 kilograms of silicon, the mold starts out on its way toward melting furnaces. The fully automated process maintains the highest purity standards and conditions. With crystallization furnace temperatures reaching more than 1,400 degrees Celsius, the silicon melts within 20 hours. After 3 days, we have produced a multicrystalline silicon ingot measuring 84 by 84 centimeters. The efficiency of the subsequent solar cells depends entirely on the quality of both the melt and the crystal structure. Upon removal from the mold, the silicon ingot is transported from the crystallization center to the ingot store. While continuing to cool, it remains in an intermediate buffer zone, awaiting further processing. The crystallized silicon ingot is then removed from the ingot store and hoisted into a so-called briqueter. This high-tech machine divides the ingot into 25 equal-sized square bricks in a cutting process which, owing to silicon's special material structure, poses a unique challenge to the tools involved in this process. A view inside the briqueter shows a cutting head with numerous deflection rollers, over which a special wire runs. The arrangement of the rollers ensures that the wire saw produces a matrix corresponding to the cross-section of the bricks. The cutting head slowly sinks downwards, causing the wire saw to cut through the silicon ingot. With rapid to and fro movements, the slurry, which consists of a mixture of silicon carbide and polyethylene glycol specially developed for the silicon cutting process, is kept in motion. The cutting process, during which the silicon ingot is cut into 25 bricks and side parts, so-called tops and tails, are removed, takes approximately 7 hours. Then it's time for a wash. fully automated computer-controlled conveyor lines transport the cut ingot pieces to the ingot washing system. This latest generation cleaning system resembles an oversized dishwasher. First, high-pressure jets blow a cleaning fluid around the silicon ingot. A blower subsequently dries the bricks. 15 minutes later, a robot picks up the bricks one by one, measures their geometric parameters, and passes them on for marking. High-tech measurement devices weigh and measure the silicon bricks and scan them using infrared rays to determine the quality of the silicon crystals. Short and efficient routes, these are the defining features of our water production workflow. As soon as the bricks are catalogued, a fully automated shelving system transports them into the intermediate store. The storage location is chosen such that bricks of the same quality are stored together. The system also combines varying brick lengths to form a uniform machine size, a so-called batch. Following a thorough sorting of the bricks, they are now ready for the next processing stage. Via the fully automatic shelving system, the pre-sorted silicon bricks are then transferred to the wafer fabrication stage. The bricks are bonded to both a glass plate and a carrier panel, a technology that has been developed and continually improved by Solarworld's experts. In the wire saw section, which comes right after the bonding center, another wire saw process is used to cut the bricks into thin discs, the so-called wafers. The high-tech saw is equipped with two large track rollers. In contrast to the bricketer, a special wire of roughly 700 kilometers length runs across it at high speed, creating a rotating wire field through which the silicon bricks are pushed. The wire transports slurry. Its fine particles slice the silicon brick into wafers that are approximately just 0.2 of a millimeter thick. After approximately 8 hours, the plant has produced between 2,000 and 3,000 wafers. As one of the largest photovoltaic companies, Solarworld not only produces wafers for its own solar cell production, but also for sales to customers worldwide. The fourth and last production stage in the manufacture of multicrystalline silicon wafers begins in a large cleaning plant. The sliced bricks, which are bonded to carrier panels, are pre-cleaned in baths to remove all slurry and saw residue. The plant then automatically transfers the bricks to an adhesive removal basin, where the bricks are separated from the carrier panel, resulting in approximately 0.2 mm thin silicon wafers. Next, the wafers are isolated and run through further cleaning lines, various surfactant and water baths, and the subsequent drying process ensure optimum surface cleaning. All wafers are then measured by fully automated sensors and cameras and graded according to their thickness and surface quality. As base elements in solar cell production, multicrystalline wafers are subject to very thorough final inspections. Aside from automatic testing procedures, the trained eyes of our staff also help ensure the high-quality standard of our products. Finally, once they correspond to all our strict quality requirements, the wafers qualify for the Solarworld logo. Securely packed, our wafers are then shipped all around the world. Again, automated processes guarantee maximum punctuality and flexibility. In as little as 8 days, ultra-pure silicon has been transformed into multicrystalline wafers for the photovoltaic industry, applying fast, energy-efficient and cost-effective processes around the clock. Each day, wafers with a total capacity of around 1.5 megawatts leave the factory, enough to cover the electricity requirement of 1,600 people and take another big step along the way towards worldwide, independent, environmentally friendly and secure energy supplies. This is what we at Solarworld stand for. We turn sunlight into electricity. Welcome to the Solarworld module production plant in Freiburg. Every day around the clock, a fully automated production process produces solar modules using 4 main production steps: layup production, laminate production, module production, and finishing. A main component of our solar modules is glass. Each day, 4 trucks deliver 100 tons of the 1.60 times 1 meter large and 4 millimeter thick plates. This safety glass is similar to that used in car windshields and is treated with an anti-reflective coating. The glass plates are fed into the production process automatically. A large washing machine cleans and dries the glass before it is processed. The purity of the glass is an important factor for the efficiency of our solar modules. In the second step, the glass is covered with a so-called EVA film. Later, this film tightly seals the cells, permanently attaching them to the glass. Latest generation computer-assisted conveyor lines intelligently control the production flow. The systems independently recognize which of the 8 production lines must be supplied with material. With this design, even maintenance work can be performed at any time without halting production. This process has been developed by the specialists at Solarworld and is unique worldwide. After they have been checked and sorted according to capacity, our solar cells arrive in the module factory securely packaged in special carriers. Here, they are again checked for any possible damage. A robot connects 10 identical cells in a chain, known as a string. The solar cells are soldered in series, on both the front and back, creating the strings, which can generate about 5 volts of electrical potential. Our employees give close scrutiny to the string before the fully automatic production process continues. 6 of these strings, laid next to each other according to the polarity, create a matrix of 60 solar cells. The cell strings are then soldered together in series, so that the module delivers a total power of 245 watts DC. Now properly mounted on filament glass, the future module is sent on to further production steps. It's given a second transparent EVA film and a very robust rear film that resists the system voltage of photovoltaic systems of up to 1000 volts without any problems. The complete package, experts call it a layup, is subjected to additional testing procedures. The electroluminescence measurement, for example, reveals possible hidden cell breakage. The trained eye of our module specialists also helps guarantee consistently high product quality. Properly sorted into groups of 4, the modules are now laminated. A look inside the laminator reveals exactly how this works. Glass, films, and cells are warmed in a first chamber to approximately 150 degrees Celsius. In the second chamber, the EVA films are melted, while the air between the films is removed by a vacuum. Solar glass, solar cells, and films form the so-called laminate. The module cools in a third chamber, and after approximately 24 minutes, it leaves the laminator as a sealed, weather and shock-resistant unit. In the following production step, our solar modules receive their patented flat connection sockets. This is a seamless process. With welded joints rather than soldered joints, it ensures maximum adhesion even under the highest loads. In the framing station, complete automation also ensures the best quality. The frame elements are given the correctly fitting corners and are filled with a two-component silicone. Pressers then squeeze the frame parts onto the laminate and slot them together with the corner pieces, forming a stable whole. The module must once again prove itself in the flasher. It passes fully automatically through a second electroluminescence test, as well as the insulation and high voltage tests. Power rating is determined, and the module is classified under worldwide uniform standard test conditions. In the final production stage, the connection sockets of our solar modules are filled with silicone, which provides protection for the contacts against corrosion and mechanical load. When everything is correct, the connection socket is sealed and the cables are attached. The rear label gives individual information on the type, power rating, and production site. A last comparison of all test results and a final visual check by our experienced module specialists guarantees the proven Solarworld quality. A robot sorts the modules according to their product and power class before they are securely packaged. The finished module pallets are transported by our logistics division to an intermediate storage site or are loaded directly onto trucks. Up to 6,000 solar modules leave our plant in this way every day. This amount would cover 1.5 soccer fields and can supply 350 houses with electricity. The production of solar modules can hardly be faster and more energy and cost efficient. And we are thinking further still. Today, our module plant already produces a large part of its own power. This is what we stand for at Solarworld. We turn sunlight into power.